it's tempting to just forget about units. But there's a good reason why those units are there. If I say walk 7 that way, you say 7 what, right? You have to have a unit to understand what a number is talking about. And a perfect example of this happened when NASA tried to send this orbiter to Mars. One team used inches and miles and things like that. Another team used meters and kilometers, and they launched a $125 million Mars orbiter basically in the wrong direction. Okay? Units are important. And because we don't want this to happen, in science, we have standard units that we use. For distance, something on this scale, you would use kilometers. Or if you were talking about the orbiter itself, you'd probably be using centimeters. That way, everyone is using the same units. You don't get this confusion going on. We have what we call the SI units. These are our base units. In terms of length, it's meter, mass, kilogram, volume, liter, time is seconds. Temperature is kelvins. You may or may not be familiar with what kelvins are at this point, but by the end of the semester you certainly will be. And then don't even worry about this week yet. But the base unit, the SI unit for number of particles is a molar. Okay. So we call these base units because we can start with that unit and then we can add prefixes onto it to change the order of magnitude. So let's look at length. You said that we have the base unit of meters. So this line here is going to represent meters. If you look at a meter stick, what are the markings on that meter stick? Centimeters. And how many centimeters are on that meter stick? 100. So a centimeter is 1/100th of a meter. In terms of 10 to the power of something, that's 10 to the negative 2. That prefix, centi, you can put centi on any unit and say that means it's 1/100th of that. This is the same exact table with mass. If I just go back and forth, what's the only thing that's changing? The G and the M. The centi, the milli, the micro, the nano, the pico, those don't change. These numbers don't change. A centigram is 1/100th of a gram. A centimeter is 1/100th of a meter. A kilometer is 10 to the third. What number is 10 to the third? 1,000. 10 to the third, that's a 1 with 3 zeros on it, which is 1,000. So a kilometer is 1,000 meters. You would take your number of meters and you would divide it by 1,000 to go to kilometers, take your kilometers, multiply it by 1,000 to get to meters. We'll do some of those conversions coming up. But I would suggest in this class, we will use kilo, centi, milli all the time. You may see micro. But you're going to want to get really familiar with milli, centi, and kilo. It's not that hard. Think in terms of units that you're familiar with. You knew centimeter. You know that there are 100 centimeters in a meter. So what is bigger, a centimeter or a meter? A meter is bigger. Picture your meter stick. Each little piece of it is a centimeter. The centimeter is smaller. You know kilometers. What's longer, a kilometer or a meter? A kilometer is meter. Keeping those things that you already know in mind are going to help you later on. So we're going to start looking at what these units actually are and how we derive them. So in mass, the first thing we'll talk about is mass. Mass is the amount of matter that we have. What did we say last week matter is?
Something that takes up space
Something
and
that
has
occupies
mass.
space. I mean,
Correct. Right. It basically, it takes up space, and matter is what makes up everything, okay? So mass, the unit of mass, is how we measure how much of that matter we have. Here in the US, we like to use pounds, okay? We go back and forth between pounds and kilograms and grams, but in science, a pound is not the same type of unit as a kilogram. A pound is weight. Kilogram is mass. Where the difference comes in is weight depends on gravity. Have you ever heard that you would weigh less on the moon? That's because your weight is dependent on how strong the gravity is. But if you are 100 kilograms on Earth, that is your mass. That's how much matter you have. If you go to the moon, you still have the same exact amount of matter. You are still 100 kilograms. So in science, we don't want to have to worry about gravity. So everything is in mass. Our SI unit is grams. When we work in the lab, we're going to be working on the gram scale. Whether it's 1 gram or 5 grams or 0.3 grams, that's the level we're going to be working on. If you work in industry and you're working in the chemical industry and you're making something, you're probably going to be working in the kilogram scale. I work in more of a biological field. We have tiny, tiny little samples. We work in the milligram or microgram scale. You basically can't even see it. You just have to trust that it's actually there. We measure mass on a balance. It's the scale, what you would call a scale in the lab. Those digital scales are actually called balances. For a point of reference, imagine one little salt crystal. The salt crystal that is in your salt shaker. That's about 50 milligrams. That's tiny. How many milligrams are in a gram? 1,000. Milli, that prefix milli means 1/1000. So 1 milligram is 1/1000th of a gram, which means it takes 1,000 of them added together to make 1 gram. A person is about 70 kilograms. How many grams is 70 kilograms? 70,000, exactly. Take that number, multiply it by 1,000. Kilo means 1,000. In my mind, it helps me to figure out whether you need to multiply or divide, is think about which one is bigger. What's bigger, a kilogram or a gram? A kilogram. So when you measure the same thing in grams, your number is going to have to be a lot bigger, right? Because your units are a lot smaller, so you need a whole lot more of them to equal that person. So if you have 7, and you know you either have to multiply or divide by 1,000, which one is going to make it bigger? Multiply. You didn't have to think about the actual meaning of anything. You just said, I need to make this number bigger. I know I have to use 1,000. If I multiply by 1,000, it's going to get bigger. If I were to divide, it would get smaller, which is the opposite of what I want. Volume is the next thing. Volume is how much space something takes up, which is another concept that you're really familiar with. For a box, it's easy. Length times width times height. Assuming they are all in the same unit. If they're all in the same unit, you can just take length times width times height. Whatever number you get, that is your volume. For volume, we use different units depending on what we're measuring. If we're dealing with solids, we normally use cubic centimeters. 1 cubic centimeter is, imagine this as a cube where the length, the width, and the height were all 1 centimeter. You would have 1 times 1 times 1 is 1 cubic centimeter. Especially in medicine, you may hear that called cc's. Someone says give the patient 50 cc stat, that's 50 cubic centimeters of whatever whatever it is they're talking about. So, what is the volume of this cube? Now, we're only given the length of one side. So if we're only given the length of one side, how can we figure this out? It's length times width times height, right? We're only given height.
It's a cube.
It's a cube, so they're all the same. That's something you're going to have to do throughout the semester. Look at the question. If you're not given something that very clearly is needed, you're going to have to figure it out. It wasn't hard to figure out, but you did have to pull that out of the question. It said it's a cube, which means all the sides are the same. So, if that's the case, how do you find the volume of that cube? 2 times 2 times 2, which is 8. 2 times 2 is 4, times 2 is 8. So what is the volume of that cube, including units?
8 cubic centimeters.
8 cubic centimeters, or 8 centimeters cubed, or 8 cc's, however you want to put it. It's all the same thing. When we're dealing with liquids, we normally don't use cubic centimeters. We use milliliters. But to make it easier, a milliliter is exactly the same as a cubic centimeter. In terms of the amount of space it takes up, it is the exact same thing. It's just taking away this cube makes the math and everything so much simpler, because in liquids, we use liters. So it's basically ability to go from one unit to another just by saying this is equal to this. Yeah?
Does 1 milliliter equal 1 cc?
Yes. So I'm in science, we do milliliters. I've always wondered why in the hospital, at least on TV, they say, give the patient 50 cc stat. Does anyone work in the hospital? Does anyone ever use cc's?
In the pharmacy.
You do?
Like, doctors write scripts with CCs, and it doesn't make sense to me why they would even prescribe it.
I guess we're not going to solve the mystery tonight.
I work for an oral surgeon, and we do anesthesia,
Yeah.
so we do CCs.
You do cc's. A cc is exactly the same as a milliliter. I don't know. Do the syringes and things that you use, do they measured in cc's or
Some.
milliliters?
Milliliters.
They're milliliters.
Mhm.
So the instant, what you're using to measure is milliliters, but the
Yeah.
doctor says cc.
Maybe we should use yourself.
Maybe they just put
I
the
mean,
oil.
he does different. Sometimes he'll say milliliters, sometimes he'll say
They'll like write
Yeah,
in
I've
the
seen some that say
instructions
CC.
CC, and then the bottle will write like 60 ml, which doesn't.
If you put cubic centimeters, I will never mark you wrong, but we use milliliters in science. So, how many milliliters are in 1 liter?
1,000.
1,000. Milli means thousand. Milliliter is 1/1000th of a liter, so there are 1,000 milliliters in a liter. We're going to do some conversions. 25 milliliters to liters. How would you do that?
Add 3 zeros to the left side.
So you are, who said that?
Okay.
You're ahead of us. So you're good with numbers, okay? So let's step back and look at it the way we were looking at it before. Okay? What number does milli go with? 1,000. Is a milliliter bigger or smaller than a liter? Smaller. So when we go from milliliters to liters, when we measure the same thing in liters, is our number going to be smaller or larger?
It's smaller.
Hmm?
Smaller.
It's going to be smaller. Okay? Think of something that you're more familiar with. Think of meters and centimeters. If you go from a centimeter, which is small, to a meter, which is large, your number is going to get smaller. Yeah.
So basically dealing with that, it's just like basically using scientific notation in a way. When you see like milliliters to liters or
Yes.
centimeters to milliliters.
You're ahead of us also.
Oh.
Scientific notation is coming up. But on that chart that we looked at, we saw the 10 to the third, right? So the way that was working 5 minutes. If you remember these exponents, you can just do that, and you can actually put that into your calculator, okay? To me, that is not, yes, that's correct. If you know what you're doing, you can do that, but it's not logical. To me, the logical way of doing it is say, I know it's 1,000, do I have to multiply or divide? I want a smaller number, so I'm going to divide by 1,000. So that's 25.0 divided by 1,000, what does that come out to be? 0.0250. Mathematically, this is exactly the same as that. Multiplying by 10 to the negative third is the same as dividing by 10 to the positive third. If you don't understand that, don't worry about it, okay? You are perfectly fine to work in this world. Okay? Yeah.
Are significant figures going to be important in the near future?
Near future is in about 5 slides, yes. But not. I did it correct. It seems like you caught that. But at this point, it's not. Okay.
Do you want us to simplify it? Like, if we just write 25 times 10 to the negative 3, can we just leave it at that? If that was ever a question on some sort of exam.
If mathematically you are correct, and you have the correct number of significant figures, which I don't know at this point whether you know what that means or not. If you're mathematically correct, and you have the right number of sig figs, I don't care what form it's in. Make sense? So here's another one. We're going to convert 25.0 milliliters to quarts. This one is not just a prefix thing. This is going from US to the rest of the world. Okay? So 25 milliliters to quarts. And we're given the conversion factor, 1 liter equals 1.057 quarts. The very first thing I would do is look at this and say, what is larger, a liter or a quart? Because it's not immediately obvious. You have to stop and think about that. A liter is bigger. Why? How can you figure that out from that?
Takes more quarts.
It takes more quarts. Exactly. It takes just a little bit more quarts to equal that 1 liter. Does everybody see that? Because I'm serious when I say that is not always immediately obvious. It's very easy to look at that and say, that number is bigger, which means quarts are bigger. It means, what that means is it takes more of those to equal that 1. Okay? So we have 25 milliliters. How are we going to get from this to quarts? How can you do that? We don't have a conversion factor from milliliters to quarts.
You make it equal to liters.
Right. We know how to go from milliliters to liters. We just did it, right? So, the second part, it tells us how to go from liters to quarts. So we know in the first step that 25 milliliters is 0.0250 liters. So the question is really convert that to quarts. So the number I'm going to either multiply or divide by is 1.057. Am I going to multiply or divide by that number? I heard both answers. So think about it. We're going from liters to quarts. Is the number going to get larger or smaller? It's going to get larger. It takes more quarts to equal what you're starting with in liters. So your number is going to get larger. Okay? So if I want my number to get larger, do I multiply or divide by 1.057? I multiply. And what does that equal?
0.026.
0.026 watts. What's my number? Quarts.
Could you also set it up as like a proportion? No.
As in multiplying this number by the proportion?
No.
You're ahead of us, that's a few slides later also. So if you're not following it this way, later today we're going to talk about dimensional analysis, which is proportions. Okay? In that way, that is dimensional analysis is math you can do without even knowing what you're doing. Okay? It creates the roadmap for you. Okay? Yeah.
With these questions, will we just go to like, if it was 0.269, will we round it up? Or will we?
That is significant figures which are coming up.
Okay.
You're all scared of the sig figs already, aren't you? Okay. So now we've talked about mass, we've talked about volume. Density is just mass divided by volume. And so conceptually, what that means is how much mass you have for a given area. So imagine you have two samples. One is water, one is lead. And they're both the same volume. Which one has more mass? Just based on your life experience, which one's heavier? The lead is more heavy, right? That's because lead is more dense. For a given volume, there is more mass in that. So the equation for density is D equals M over V, DMV, okay? This you're going to use over and over again. Actually, here's your little cheat sheets. After today's quiz, you will have this cheat sheet for every quiz and the final exam. Okay, the only reason you don't have it today is because you don't need any equations, and it has a periodic table on the back which you're supposed to memorize. Okay, so after today, you will have this. What I'm looking to see is whether this density equation is on. It is not. So this is an equation you're going to have to memorize, but it's not difficult, and you're going to use it so many times that you probably won't have to work at memorizing it. Density has the units of grams per milliliter if you're working with solids or liquids, or if you're working with a solid, it'd be grams per cubic centimeter, which is the same thing as a milliliter. If you're working with gases, they're very low density, so we have to go grams per liter. We have to have a much larger volume in order to get a number of grams that are actually measurable. So looking at this graduated cylinder, we have these layers here. Why are they separated? What about density?
They're all different densities.
They're all different densities, so they find their own level based on their density. Which one of these layers is the most dense? The bottom. It's just like when you put that lead in the water. The lead sinks. Lead is more dense. Dense goes to the bottom. So just going up, each one is sequentially less dense. That is the least dense of all of them. We're going to do this in lab, I think it's next week. These are just some examples of what densities are. Helium. You know that helium balloons float, right? Why do they float? Think about this, but here.
It weighs oxygen.
The helium is less dense than air. So the less dense thing goes up. You can also think of it as the air sinking to the bottom. And when it sinks, by default, the balloon has to go up. Oxygen gas is slightly more dense. Oxygen is part of air, which is what makes air more dense than helium. Cooking oil is a huge jump, right? You went from gases to liquids. The liquids are much more dense because the atoms are a whole lot closer together. You know what happens when you mix oil and water? The oil floats, right? Oil is less dense. Oil floats. Mercury is a liquid, but it's a metal. It is very, very dense for a liquid. When we go from this liquid to a solid, again, it gets higher density. But when we start looking down here, these are actually less dense than the liquid mercury, right? So in general, solids are more dense than liquids, but there are certainly exceptions. It really depends on what type of sample you have. Yeah.
I'm just curious what, like with mercury, what keeps mercury in a liquid state when it's metal? I mean,
It has to do with the interactions between the atoms. Mercury is right there. The electrons behave very oddly in mercury, and so it makes the atoms behave weirdly around each other. That's a future lecture.
Is it boiling like that? Melting point rather?
It is, but the melting point is determined by those interactions. So we had our cube, right? We already found the volume of that cube. The new question is, what is the density of the cube? And so, what is the equation that we're going to use? D equals m over v, right there. So what is it that we're solving for? So we have three variables, density, mass, and volume. What is the one we're trying to find? Density. So we don't know v. Now it's just a matter of plugging in the two other numbers. What is the mass of that cube? 11.2 grams is given to us. What was the volume of that cube? 8 cubic centimeters. So you do the math, and that equals what?
1.4
1.4.
G over S.
So this is a solid, so we're going to use cubic centimeters. If you did milliliters, it wouldn't be wrong. It just would be odd. Grams per cubic centimeter. On the slide we introduced density, we said that solids use grams per cubic centimeter. And it makes sense. What does this slash mean in math? Over, which in terms of what you put into a calculator, what is that? Division. Grams divided by centimeters. Okay? We can do that math with numbers. We can't do it with letters. So the letters just move down here. It's the same thing. That's where that unit comes from. Did that. How many people have swum in the ocean? How many people of those people have swum in freshwater? Have you noticed the difference in your ability to swim in the two? A little bit. Is it easier to float in the ocean or the freshwater? Just by your experience. Saltwater, actually. So this is the Dead Sea. Okay? The Dead Sea is about the most concentrated salt water, at least natural salt water, on Earth. It is really, really, really easy to float in the Dead Sea because it has so much salt in it that it's more dense. So if I go into a lake, and I go into the ocean, and I go into the Dead Sea, my density is not changing, right? What determines whether I sink or float in each of them?
Density of the salt water.
The density of the water, because if I am more dense than the water, do I sink or float? I sink. If I'm less dense, I what? I float. But I am made up of a whole lot of water. So my density is very close to the density of freshwater, saltwater, and the Dead Sea. So generally, that line falls between the freshwater and the saltwater. A lot of people will actually sink in freshwater. They're sort of neutral in saltwater, and then they float very easily in the Dead Sea. Now, your results may vary as mine do. It depends on your body mass index. Fat is less dense, so I float in freshwater. You may or may not. I don't know. So here are two cubes, okay? This is an unintentional optical illusion, okay? These two cubes are actually the same size. Do you see them as the same size or different sizes?
Pretty similar.
Really? I look at that and I say that one is clearly smaller.
Yeah.
It looks a little smaller.
But
I see the opposite. I think that one.
You think this one's smaller?
No, I think aluminum looks larger.
Really?
Wow.
It may be the projector.
maybe. Anyways,
Say on the paper.
they are, believe it or not, I actually did check it, and they are drawn the same size. These are the same size. The question says, the cube of gold has a greater mass. So this one, gold, AU, hopefully you know that, is more, it has a greater mass than the cube of aluminum, which is Al. Which cube has the greater density? Gold. If we look at our equation, D equals M over V, the V is going to be the same for both of them, right? In terms of math, if you increase the mass, what happens to your density? It goes up. Density and mass go the same direction. So the one that has the higher mass has the higher density, and the question tells us the gold has a greater mass. So the gold has to have the higher density, because it has to fit that mass, the more mass, within the same volume. Here's another one. This says they have the same mass. Which one has the greater density? Again, it's gold and aluminum. Why?
Because they're the same mass, but that one has to fit into a smaller space.
Right, it's the same principle, but just mathematically we're working with the bottom of the equation instead. So it says they have the same mass. So here, the top of our equation is not going to change. So when volume goes up in this equation, what happens to our density? It goes down. Volume and density go in opposite directions. So the one with the largest volume has the lowest density. And aluminum clearly has the larger volume. Make sense? Questions? Have you ever noticed this? Regular Coke sinks, Diet Coke floats. Why? Regular Coke has a higher density, exactly. Why? It has all of that sugar dissolved in it. It's just like regular water versus salt water. Once you dissolve the salt in it, it becomes more dense. Regular Coke has a whole bunch of sugar dissolved in it. The artificial sweeteners in Diet Coke are much, much, much sweeter than actual sugar. So you don't need nearly as much of it for it to taste just as sweet. So Diet Coke floats, regular Coke sinks. So if you go to a cooler and it's mostly water, and some ice, and you want a regular Coke, you're going to have to dig down to the bottom. Bring this to another question. Imagine that same cooler. It's mostly water, but there's still some ice left. Where is the ice? At the top. But we said in general, solids are more dense than liquids. So why does ice float?
Because air pockets in crystalline structure.
It could, that could be, yes.
It's less dense than the water it's in.
It's less dense than the water it's in, but why?
The higher volume, the same mass.
It expands, doesn't it?
Expands and freezes.
Water, you know that. You know that water expands when it freezes, right? If you put a full water bottle in your freezer, what's going to happen? It's going to blow up, okay? Water is a special situation. In general, we say gas is like this, liquids like that, solids like that. That has more mass per area than that does, so the solid would be more dense, like that, yes. So this is liquid water. You're randomly, the atoms are moving around randomly. Ice makes a very ordered crystal. Now, crystal is a specific pattern that the atoms will always make when they freeze. In the ice crystal has a whole bunch of dead space in it. Do you see that? So actually, when these atoms rearrange to make that, they move apart from each other. When they move apart from each other, they become less dense. Do you see that? Temperature is another thing you're very familiar with. Temperature is measuring how hot something is in terms of a standard. Someone decided this is where we're starting our temperature scale. Okay? Celsius is logical. What is 0 Celsius?
Freezing point of water.
Freezing point of water. What is 100 Celsius? Boiling point of water. So someone developed Celsius based on water, something we are all very familiar with. What's the boiling point of water in Fahrenheit? 212. What's the freezing point of water in Fahrenheit? 32. Does that make any sense? Not really in our world. We measure temperature with a thermometer, okay? Or if you want to get really scientific and impress people, call it a thermometer, okay? That's really what it is. In science, we use degrees Celsius or kelvins. These are the conversions, okay? These are on your cheat sheet, okay? So on the cheat sheet, it tells you how to go. It gives you this one, and it gives you these two also. So you don't have to memorize your temperature conversions. You just need to know how to use these though. You don't want to come into the quiz or the final exam not having used these equations. So these are our three scales. Celsius is the one that we use most in science. And we also say it's the most logical, with 0 being freezing point of water, 100 being boiling point of water. Kelvin is different. 0 Kelvin is a logical number. It's not in real life. Does anybody know what 0 Kelvin is? Yeah.
Absolute zero.
It's absolute 0, which means what? Yeah.
All atoms stop it.
Atoms stop moving, which is the absolute or complete lack of heat. If there is 0 heat, you are at 0 Kelvin. So that's why this one is logical. Just in real life, we're nowhere near 0 heat. So we work with very large numbers in Kelvin. So it's a little more clumsy to use Kelvin, but it's just as logical as Celsius. I honestly don't know where Mr. Fahrenheit came up with the scale.
100 was supposed to be human body temperature.
Was it? So they were not very accurate in their measurement.
I mean, it was like, I want to say the Sumerians.
So they would kind of have a disadvantage.
It's still a lot. Room for improvement.
Okay. So apparently that's where it came from. Thank you.
I'm no zero though. I'm no clue.
So we talk about precision versus accuracy. So I said that when they measured that body temperature, they were not very accurate. I did not say they were not very precise. Precision and accuracy in science have very distinct, separate definitions. And they are not the definitions that you normally use or hear about in everyday life. They're very similar. But if you pay attention to how people use these words, they use them more or less interchangeably. And for us, they are different. Precision is how repeatable a number is. If you take a measurement 50 times, and you get all your numbers are very, very close together, we could say that that measurement is precise. If I measure my height 50 times, and every time I say I'm either 2 foot tall or 2.1 foot tall, that's pretty precise. Okay? It's completely wrong, but it's precise. It's very repeatable. Accuracy is how close you are to the actual value. So if I measure myself 50 times and I get 2.0 or 2.1, it's very precise, but it's not accurate. And where it gets just a little bit more confusing is when you take a bunch of measurements, the accuracy of those measurements as a whole is determined by the average. Okay? So it's very useful to think of these precision and accuracy in terms of a dartboard. So here's a dartboard. These are your darts. Would you say that that is precise, assuming you're aiming for the middle? No. Why?
There's only like one.
Shows the atom dots on. Got a large spread.
Precision is reproducibility, how repeatable it is. It's very large spread. This measurement is nowhere near that measurement. So this is not precise. Now we completely forget about what we said about precision. Now it doesn't matter. We move on to accuracy. Is this accurate?
Depends on what you're aiming for.
Assuming you're aiming for the middle,
Oh.
this is what I meant by it gets a little confusing. In your mind, try to figure out the average position of those.
The average is in the yellow, right? Is it more in the yellow?
Well, I would say that one and that one are kind of opposite each other. You see that? So what is the average position of that point and that point? Right in the middle.
Also design.
So if you kind of look at it, the average position there is more or less in the middle. Do you see that? Yes, there are more on the left than on the right. So our average is probably going to be about here. But if you're throwing a dart, you'd probably be pretty happy with that. So this is actually accurate. Even though most of your points are nowhere near the center, the average is close. So that is an accurate throwing. Okay, I guess when I wrote this, I said I was not happy with this. Okay? There must be an even better one coming up. What about this one?
It's precise, but not.
Precise, but not accurate. It's a very tight grouping, but the average is clearly somewhere in here, which is nowhere near the center. That one's easy, right? What about this one? Precise and accurate. You have the tight grouping and the average is in the center. Now, what about that one? Apparently when I made this, I thought that one was better than that one. So that one is accurate, but not precise. Okay. You would not have something that ambiguous like on a quiz or an exam. Okay, it would be probably one of these three, something like that. It would be obvious. If you saw that, what would you, on a quiz, what would you do after you wrote an answer? What would you do? Explain it. Okay. Anytime you question whether you're reading it right or you think there's multiple ways to interpret it, write your explanation. A couple more conversions. You're going to be doing a ton of conversions in here. Convert 12 grams to milligrams. What's bigger, a gram or a milligram? A gram is bigger. So when we convert it to milligrams, is the number going to get larger or smaller? Larger. Because milligram is smaller, so we need more of them to equal what we're starting with. So we have 12.0 times what? 1,000. 1,000 is the number we're dealing with because it's milligrams. So we said we want our number to get bigger, so we're going to multiply by 1,000. So that is 12,000 milligrams. Next one is 12 grams to ounces. So again, we have 12.0 grams. Look at your conversion. What is bigger, an ounce or a gram? An ounce is bigger. It takes 28 of our grams added together to equal 1 ounce. So we have, we're going to say 28.34 multiply or divide? Divide. Why divide?
Numbers get smaller.
We want our number to get smaller. When we go from grams to ounces, an ounce is a bigger thing, so we need fewer of them. So we're going to divide by 28.34, and what do you get?
0.423.
423 ounces. Now we get into the mess. Sig fig mess. That is the correct answer. 0.423. If you said 0.42 or 0.4234, those are not correct. Even though you would think that one is more correct than that. Because of sig figs, significant figures, and these are going to be the bane of your existence for the semester. Okay? I do not know a chemist, I do not know a scientist who likes significant figures. Okay? It's just what we have to do in chemistry. This actually happens, and it'll, even though you don't do lab reports, in this class, I guarantee you at some point you're going to spend 15 minutes on a problem that you're stuck on. You're going to figure it out, you're going to be so proud of yourself, you're going to turn it in, and you're going to lose points for sig figs. Because you said it was 0.4234 instead of 0.423. Okay? Significant figures. There are a bunch of rules on determining whether a number or a figure is significant. Easiest one is if it's something other than 0, it's significant. 435 grams, all those are non-zeros. So all of those digits are significant. That's the easiest one. If you have a 0 that falls in between two non-zeros, that 0 is significant. So in 405, that 0 is significant. In 40.5, we ignore the point that 0 is between the 4 and the 5. It is significant. If you have zeros to the right of a non-zero and to the right of a decimal point, it is significant. They are significant. So there are 3 significant figures in that number. Both the zeros are significant. If you have a 0 to the left of the first non-zero, like that 0 and these 3 zeros, they're all to the left of the first non-zero. Those are not significant. If you have a number that's more than 1, so you have 1, okay, so you have 1 point something, or you have 100 and something. The zeros after that non-zero may or may not be significant. You're going to have to look at it. 400 and 400. If you did that on a homework problem, one of those numbers is going to be correct and one of them is incorrect. It's all going to depend on how many significant figures you need. How many significant figures do you think are in that 400? 3 and 4. What about 400 point? I heard 3 and 4. Okay. When you have a decimal point like that, it's counting, it is signifying to you that the zeros between the non-zero and the decimal point are significant. There's no point here, so these zeros are not significant.
Say that again.
When you have that point there, that tells you everything between that point and the non-zero is significant. If you don't have a point, everything between where that point would be and the non-zero is not significant. So this has 1 significant figure, the 4. That's it. It's not 2, it's not 3. It's just 1. How many does that have? 3. They're the same number. They're both 400. But this one has 3 significant figures. This one has 1. You have to figure out how many significant figures your answer is supposed to have. Before we do that, let's get some more practice. Here's a number. How many significant figures are in 26? 2. That's as easy as it gets, right? There are 2 digits, two figures, and they're both non-zero. There are 2 sig figs in 26. What about that number? 5. So clearly there are at least 5, right? You have to figure out whether those zeros are significant. Are they?
Zeros to the right of the decimal
Oh, yeah.
point.
Zeros to the right of the decimal point and to the right of a non-zero are significant. So in this case, they are significant.
Well, where do you draw the line? You can just draw another zero and call it significant.
You could, but your measure, we'll talk about where these number of sig figs come from. There is a set number of sig figs that that number is supposed to have. So if you put a extra zero on there, you have the wrong number of sig figs, it is wrong. Okay. Yeah.
On that problem that we did,
Yep.
were there be 4 significant figures?
This one,
Yeah.
we'll see. There actually is 3,
Okay.
but we're going to talk about that. And when I say you get the question wrong, don't worry, it's lenient. Okay, it's not all or nothing. It's just a little tiny slap on the wrist, basically, saying you got the sig figs wrong. Don't do it again. I have to take something off, but it's not going to hurt you. What about this one? How many sig figs are in that number? 4. But these zeros are to the right of the decimal point.
But they're to the left of the first significant.
Right. But they're to the left. This 3 is the first non-zero. They're to the left of that first non-zero. So they are not significant. Here, they were to the right of non-zeros. Here, they're to the left of non-zeros. So they are not significant. Yeah.
So the answer would just be 3416?
Well, it would be, those 4 are significant, so the answer would be there are 4 significant digits.
Oh, okay, so it won't never be a question with that answer, and you would have to figure out, write it in the right sig fig form?
You would have a math problem like this,
Okay.
and where it's easy math. The
Okay.
tricky part is how many sig figs does your answer supposed to have?
Okay.
So would you just write 0.3416
Yeah,
in
that's
that
what I was gonna
aspect
say.
instead of doing the zeros?
No, we'll get here. But if you did math and you decided your answer was supposed to have 4 significant figures, okay? And you would put that, if you put 0.3416, that's a very different number,
Yeah.
right? You cannot change the number. You can only change the number of significant figures. So if your problem told you, one way or another, we'll see, that you had to have 4 significant figures, that is correct. There are 4 here. This is scientific notation. That's a kind of upcoming slide, but you don't have to understand scientific notation to figure out how many sig figs are in scientific notation. Ignore this portion. Just look at that. There's 1 sig fig, okay? It looks scary at this point, but how many sig figs are in 9? 1. How many sig figs are in this big monster?
8. So basically, sig figs are numbers you can't replace with scientific notation.
Correct. So there are 1, 2, 3, 4, 5, 6, 7, 8. And in terms of sig figs, we completely ignore that times 10 to the negative 7.
So that 0.0034 could be written as 3.4 times 10 to the negative third. That's why the zeros.
It could be written 3.416 times 10 to the negative 3rd. Yes.
I'm sorry I said your base. So
now we have to figure out how many sig figs we have to have. Okay? Multiplication and division is the easy one. And luckily, this is the one you'll use by far the most often. Okay? In multiplication and division, you take however number of sig figs were in your starting numbers, figure out the lowest number, and that's how many your answer has. So how many sig figs were in our 12.0? 3. How many were in 28.34? So how many does our answer have? 3.423. Okay. Like I said,
You said that the most sig figs
Least.
or the least? Okay.
Least.
Okay.
least. Yeah.
Wouldn't that not matter because it's a conversion factor? It's a definite unit of conversion.
Yes. Yeah. But we'll come back to that. Yes, you're good. Okay. So it's multiplication division. Find the least number. If you had the mother of all multiplication and division problems, okay, there were 100 things multiplied and divided by each other. And the first number was 1, and everything after it was 1 point something. Maybe there's 50 decimal points. How many sig figs does your answer have? 1. Okay? Because that very imprecise 1 cancels out the precision and how good of a measurement you did on everything after that. That 1 has 1 sig fig, so your answer is going to have 1. So 2.06 times 4.3 is 8.853. Is that correct?
No,
Why?
because 4.3 is 2 centimeters.
Right. So 4.3 is 2, so our answer can only have 2. If you write 8.853, that is not the correct answer. What is the correct answer, David? 8.9. How did you get from 8.53 to 8.9? You rounded. Okay? And you're going to round just like you always round. You've been rounding since probably first grade. I don't know when you learned rounding, but we're going to say it's first grade. Round just like you know how to. Round to the point that's going to give you the correct number of sig. What is 6.0 divided by 3.00? Just in your head, very quickly. It's 2, right? But you can write 2 as 2, 2.0, 2.00, 2.000, 2.00000. They're all 2. You have to figure out which 2 is the correct one. 2.0. That has 2 sig figs, that has 3. So our answer has to have 2. So you say to yourself, how can I write 2 with 2 sig figs? 2.0. That 0 is to the right of the decimal point and to the right of the 2. And if you haven't figured out yet, I always write on a downward slant. Even when I write 2.0, it's not even straight. So, for what, how do I want to start this? Put somebody who has a calculator, put that in your calculator. If you can do it in your head, kudos.
It's 4.49.
So read it off. 4.4938
27.
It's a whole bunch of stuff. How many sig figs does my answer have to be? 1. So how do I write that with 1 sig fig? 4. So 4 times 1.1234 equals 4. You did nothing. Right? That's science. You can work all day and have nothing to show for it. What about 5.0 times 2.0? 5 times 2 is 10, right? How many sig figs do I have to have? 2. So I know it's 10. How do I write 10 with 2 sig figs? 10 point. Okay? Not 10.0, not 10. 10 and 10.0 are both wrong. Okay? And you very quickly, probably on this homework, that's due next Tuesday, you'll find out what happens when you get sig figs wrong. Okay? Something special shows up on your homework. You'll find out. Then I will show you. You know, I don't know, I'll buy you a Coke or something. If you can go the entire semester without getting sig figs wrong once,
To buy a Coke.
I'll buy you a Coke.
I don't know, that's insane.
Okay. Addition and subtraction is the painful. Okay? Even though you learned addition and subtraction in first grade and multiplication and division in 3rd or 4th grade, in here, addition and subtraction is the one you don't want to have to do. Okay? because you actually have to do it longhand. You have to set it up longhand. You can't just type everything into your calculator, get a number, and then figure out where to round it. You have to set it up longhand. So we have, we have 234.506 plus 0.12 plus 4,455.9. Add them all together. Okay? You're going to line up the decimal point. That's your first start. You would do that anyways if you were adding and subtracting long. Line up your decimal point, and then find the number where the last significant digit is the furthest left. In this one, which number has the last significant digit that is the furthest left? The last one. The last significant digit in this number is here, and this one is here, and this one is here. Draw a line to the right of that 9. That's your last significant digit. Draw a line. Do the math just like you always would, and then round to the left of the line. Okay. Because you do multiplication and division so much more often in here, you're just going to breeze right through this. You're going to say, that one has 263, my answer is 266. That's not correct. You have to line it up. It's a pain in the butt, but you got to do it.
Let's say it was 44,000.
So 44. So we can write 44,000 multiple ways. How are you writing 44,000? Like that? Like this?
Yes.
So we would have the decimal point we're imagining it here. But if we sorry?
Need one more zero.
Thank you. Decimal point, we're imagining it here, but we can't write it. Why can't we write it? Because it would make all these zeros significant, so we can't write it. So we're imagining in our head, decimal point is here. So now we have 0.12, and we have 234. 234.506. Where is that number going to get drawn? Where's the line going to get drawn?
That's the 44.
Right along the decimal zero.
Where is the last significant figure in this number? 6. Where is it in this number? 2. Where is it in this one? 4. That 4. Draw your line. Do your math. You're going to get 44.2 something. What can you already see is going to happen?
Round down.
That's going to round down. So you did all this math, and again, you got nothing to show for it. You're at 44,000. Yeah.
So if I'm looking at this question right here, and you see that the 0.12 is only 266, and all I would have to do is just do 44 plus 2, and I get my answer.
Say it again.
Like, it's only, the lowest one is 266, right? The 0.12,
Right.
right? Okay, so all I have to do is just draw the line of where the 44 and the 2 is, and that's my answer? Or
It's far about the other problem right here.
This one.
Okay, I don't know.
The number of sig figs doesn't matter.
Number of sig figs, in addition to subtraction, number doesn't matter.
Okay,
The position matters.
okay.
It's how many digits you have, not the number.
Okay.
So when you draw the line, you just do the math that's to the left? You don't worry about the
Well,
right side?
You would have to do the math. You would do 4, 44, 2, 3, 4 point,
Yeah.
blah, blah, blah. But I didn't have to do it because I knew what's down when it's down here is it's not going to matter. Because this 2 is going to round down. Does that make sense?
Yeah, sort of.
Sort of. This is something, you're not going to know whether it makes sense until you try it. Okay? So on your homework, try it. If you don't get it, we're gonna do a ton of this in the lab on Thursday. This is gonna make you beat your head against the wall in the lab on Thursday.
You said to do longhand addition, subtraction like that, but if you did in the calculator and just note it down, you know, realize which one had the furthest right non-zero in the way the last number counts there.
If you don't write this up like this, you can get it right, but you're asking for yourself to make a mental error.
Okay.
Okay? You can write it out longhand, but then do the math in your calculator and then just write it here. You don't have to do the whole 6 plus 0, 0 is 6, 2, and then carry the ones and all that jazz. Okay? You can do the math in your calculator and write your answer at the bottom. Make sure you put the decimal point in the right place, and then you can round based on your line. Here's another nasty one. Let's do this one. Got 587.362708, 4.36 plus, and then a minus, wow, 0.329829. 92789, that's a minus. So this is one that I would suggest not actually doing the math longhand. Because as far as I know, there's no way to do this in a one step longhand. You'd have to do it in 2 steps, plus and then the minus. If you do it in your calculator, you can do it all in 1 step. Somebody put that in and tell me what the number is.
Negative 928331.
Okay, so let's start at decimal point. Okay, what's the digit to the left of decimal point?
1,
1, 3,
3,
3,
8, 2, 9.
9, that's negative, you said. What's to the right of decimal point?
5, 5, 6,
5, 5, 6, 2. So now if I draw my line, I can round. Where does my line go?
5 and 6.
Does everybody see why the line is going to go there? The last sig fig in this number is here, and this one is here, this one is here. That one's the furthest left. So you draw the line just past that, and so I round to the left of that line. So does that round up or down? Up. 0.62 or 62 rounds up. So I have negative 92831.56. You see why addition and subtraction is much more painful than multiplication and addition. Let's take a break here. We will start 2 minutes before 7:30 on that clock. So 7:28 on that clock. That's 10 minutes from now. And if you have your written homework, you can put it in a pile here. You can do it now, you can do it at the end of class. Doesn't matter. Any meeting we have, so what I do is if you can get it to me by midnight tonight, I will count it as on time and give me the hard copy the next time you see me, and I'll grade it then, and it'll be on time.
So you would want,
Do you have a way to access it?
I would have to work with it because it wasn't allowing me to access eSanta Fe because of contact needed to be updated, and then when I went to update it, it told me the service is not available, please try again later.
Okay.
So I don't know if I can solve it immediately.
Okay. You have access to Canvas.
That's how I was trying to access it on my computer.
Okay, so if I would send you the file through Canvas, you would be able to get that.
I can't access Canvas at all, because it stops me at the same thing website about contact information. So I don't even see the course information.
Do you have a Santa Fe email address?
No, I have two personal emails.
Okay. Before you leave today, see me and I'll email you the file to your email address. And then if you can get it done tonight, this one there's no math in. You may be able to just do it right on the file, email it to me. Okay. And then print it out and bring it out there. Observation. It's okay, just make sure you tell me which one. That's fine.
Do you have to stay with possible? It's okay.
It doesn't have to
I'll
stay.
just write my name on both of them.
Okay. So, those of you that submitted this online early for feedback on the last question, I don't know if any of you in here currently did that or not. Were you able to see the feedback that I gave? Did anybody do that? I said nobody in here did that.
Actually, you have to use PDF, you said? Because you have to pay $8 a month for it, so.
Originally, I thought I was going to need it to be PDF. In order to draw, what I wanted to do, I want to be able to draw on it on Canvas. And I was going to do it on my tablet, okay? And it says to be able to draw on the file on Canvas, it has to be PDF. When I went to do it, apparently Canvas is not tablet compatible. So I can't draw on it. So what I have to do is draw on it on my tablet, not in Canvas, take a screenshot. So at this point, it doesn't matter what you upload it as. If it tries to, I think I may have told it that only accepts PDFs though. If you have that problem, it won't take your document, Word document, whatever, email me, tell me this is not working, and I'll get rid of it.
I was gonna send you mine, but when I said PDF $8 a month, I'm like, no, I can't do
No,
that.
at this point, as long as it will accept it and I can see it,
Okay.
now it doesn't matter what file that is.
Yes, sir.
It's more work on my end than it was supposed to be.
Can I do it to the post lab also?
Post lab, you turn in hard copy.
Oh, I mean, I guess like for the week, it says assignments for post lab, so. I don't know if I could do the same thing, feedback or care.
No, it's just for the last question on the homework.
Okay.
Because you're gonna come in and do a very high stakes version of it on the quiz.
Mhm.
That way you can get some feedback, you know whether you did it right or wrong before you do it on the quiz.
Yes, sir. Thank you.
Did everybody see that rain at about 3 o'clock today? Apparently that is the extent of hurricane. That's it there. It's going north. That might be all we get from it. No hurricane day.
1030.
So, yeah, I think I got it down.
Now, is there anyone in here that submitted the homework question early for feedback?
I submitted mine online, so.
Yeah. So, were you able to see the feedback that I gave?
I mean, I think I submitted it at like 1 this morning, so I don't know.
I did it. I corrected it, and I think I said, please turn it in by 5 on Monday.
Alright.
But I'm not going to hold you to that unless it's a problem if I go to bed and then I'm really busy at work. I can't get
Well,
it.
the only reason I submitted it online is because I couldn't print it off, so. I mean, I wasn't really looking for too much feedback.
Even if you submit it online, submitting online is just for the feedback on the last question.
Oh.
If you're still expected to turn a hard copy in.
Oh, okay.
But it's first week, and so because I have your electronic copy, I will come on time. Do you have a way to print it out?
Yes.
Or just, you can even just copy your answers on a separate sheet of paper?
Well, I have a way to print it out, it's just my sister was sleeping, and I don't want to print it off and take her up, so.
So I have your file. It'll be on time. Bring the hard copy on Thursday. That way I can correct that and give you your corrected copy back. Whereas if I just have an electronic copy, it's hard for me to give you that back.
Okay.
So-
Also, I looked up what I was talking about earlier, and it increases the rate of corrosion, which is why you're not supposed to do it, which is why it's confusing. Because I used to have to clean airplane quotes, and you can't use like brass and all or copper. or anything.
If you do submit that file early, what I do is I take a screenshot of that question, and I can draw comments on it, and then I upload that screenshot back into Canvas. So if you do it, you need to find that screenshot. It's in the comments for your submission, and that will have your feedback on it. Unfortunately, it appears in order for me to be able to accept files, it has to show up in the gradebook. I think, did I mention that in an email to everybody, that it's showing up as, or the, no. So if you click assignments, this is where you would submit it. There's homework 1 through 13, but then there's all this other stuff under here. Canvas doesn't allow me to separate these out, so there's nothing to submit for anything below this homework 13. Just ignore it. And then I think also in your grade book, it shows a check mark as a completion for this homework. So if you didn't turn it in, it's going to show as incomplete, but you didn't have to turn it in. And Canvas doesn't allow me to not show that in the grade book. When I took it out of the grade book, that's when it turned out it prevented you from uploading files. That's what that confusion was. In your grade book, there are going to be 2 columns for homework 1. There will be the complete, incomplete, which is completely irrelevant, and then another column with an actual number grade. Yeah.
Things to do say with the hard copy and choice.
The multiple choice, no.
Oh, okay. I
No,
heard that wrong.
because that gives you, right then it gives you feedback, whether it was right or wrong, and it tells me how many you got right or wrong. So I'll take your grade on that, plus your grade that I figure on the hard copy, and give you a total overall homework grade that goes into the grade book. Can you tell, are we missing anybody? One.
He was on the phone,
Well, it's past the time we said, so we're gonna start. So how many have experience with scientific notation? Half, 2/3 looks like. That's good. So scientific notation is also, you can also call it exponent notation or something like that. Basically, we have a number, any number between 1 and 10. It cannot be over 10, it cannot be less than 1. You can't have point something, you can't have 11, you can't have 1500. It has to be 1 to 10, anywhere between those numbers. So we have a number times 10 to the n. And n is an exponent, and it has to be a positive or negative integer. What is an integer? Whole number, exactly. So n has to be a whole number. You can't have 10 to the 2.2. You can have 10 to the 2, you can have 10 to the negative 2. But you have to have a whole number for n. The way you figure out C is you put the decimal point to the right of the first non-zero. So if I have 1084, what is the first non-zero decimal? The 1. So where is my decimal point going to go? To the right of the 1. Does this number fall between 1 and 10? Yes. If you put that decimal point to the right of the first non-zero, it is always going to fall between 1 and 10 by default. You cannot possibly not fall between 1 and 10. To figure out n, you look at how many places you moved the decimal point to get it there. So we started with 1084. Where is the decimal point in that number?
After the 4.
After the 4. It started here. How many decimal points did I move it? How many places did I move the decimal point to get it here? 3. I went 1, 2, 3. And that is how you do it. Everyone counts decimal points, okay? I should see you on a quiz taking your pencil, probably tapping numbers. When they go up here, they're probably going to be going like this, okay? That's how most people have to do it to keep track. Einstein would probably count decimal points like that, okay? No shame in it. Draw it if you have to, okay? No shame in it. So we moved 3 places to the left. So my scientific notation, we have 1.084 times 10. We moved 3 places, so it's a 3. We just have to figure out whether it's a positive 3 or negative 3. If you move to the left, it's a positive number. Think about it in a calculator. If you put that in a calculator, you're going to get that. You're multiplying this number by a big number, by 1,000. It's going to get bigger, that you're going to turn into that. When you move the decimal point left, it's a positive number. When you move it to the right, it's a negative number. So if I have 0.084, where does my decimal point have to end up? Between the 8 and the 4. To the right of the first non-zero. So I have 8.4 times 10 to the what? Negative 2. I went 1, 2 to the right. So it's 2, and I went to the right. So it's negative 2. That is scientific notation for that. So look at this number. Are you going to move the decimal point to the left or the right in that number? Left. So is my scientific notation, is my exponent going to be positive or negative? Positive. So where is it going to be? I have 3, 2, 4, 5.
It's gonna be able to take that 3 and 2.
Has to go there. Times 10 to the third. I went 1, 2, 3, but 3, and it was to the left, so it's positive. How about this one? Am I moving to the left or the right? Left or the right? The right. So it's 3.245 times 10 to the negative 6. What about this one? Am I going to move it to the left or the right? Left. So it's 3.245 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. This one, left or right? Right. So it is 5.0607 times 10 to the negative 3. 1, 2, 3 is to the right, so it's negative. What about 88? To the left, so it's there. So it's 8.8 times 10 to the first. It's 8.8 times 10. 88. About 2.45. Move it to the left, move it to the right. Keep it there. So, if this was a problem, you wouldn't have to change it. If you really, 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 really wanted to write times 10 to the something, what could you do? 10 to the 0. 10 to the 0, or anything to the 0, is 1. If you multiply something by 1, you change nothing. So 2.45 is equal to 2.45 times 10 to the 0. You never need to write times 10 to the 0 for me. And in actuality, unless a question is asked directly asking you for scientific notation, you don't have to use it for me. If you put that in your calculator, and that's what you get out, you can write it that way, or you can write it in scientific notation. Doesn't matter to me, as long as you have the correct number of sig figs. Okay? But if pay attention to the question. If the question specifically asks for scientific notation, you have to give it to me in scientific notation. Doing this in your calculator is going to depend just on your calculator. They're going to be different. Okay? You can put it into your calculator just like that. You can put 1.084 times 10 and then raise 10 to the third power. In a calculator, you would probably do 10 to the third power by 10 with a caret and a 3. Okay? The quicker way to put these scientific notation numbers in your calculator is with EE or the EXP button. Okay? 10 to the, let's do, 3.245 times 10 to the third. If we wanted to put that into our calculator, we could do 3.245, and then I think Texas Instruments generally have an EE button. You see that? Anybody who has one, can you see it? It's probably 2 little lowercase e's, like that. 3. That EE or that EXP means times 10 to the. So you would put it in your calculator like that. What you do not want to push is a lowercase e. That is something completely different. If you do that, you're gonna get not even close to the right answer. Okay? If you can't figure out how to do it shorthand in your calculator, bring it up to me, we'll figure it out. Or you can always put it in this way. If you put it in this way, you're asking for trouble in terms of order of operation. If you put a whole bunch of numbers in your calculator at once and hit enter, it may do things out of order. You can always fix that by putting that in parentheses. Okay? I don't remember what lab it is, but there's a lab coming up that half the class is going to get the wrong answer because your calculator does the wrong order of operation. It's just a matter of putting in those parentheses. So, how would you put this in scientific notation?
Decimal. 9 places to the left.
9 places to the left. So it's going to end up here. Okay? When we go from regular notation to scientific notation, we cannot change the number of sig figs. We cannot change them. So, what's going to happen when I write that in scientific notation? You're going to have to keep everything. So the idea of scientific notation is to make less that you have to write. But in this case, you're going to write 9.000000655. Now I actually have to keep those 2 zeros on the end also. They're significant. So 0 times 10 to the, times 10 to the 9th. So all I did is I made myself more work. I had to write the same number times 10 to the 9th. So you have to keep in mind your sig figs. You have to have the same number of sig figs after as before. What's this one going to be? 8.34. How many sig figs are in that? 3. So you're going to have 8.34 times 10 to the 1, 2, 3, 4, 5, 6, and it's negative because we went to the right. You cannot change the number of sig figs. These two are pretty easy. We know how to do that now. Let's look at this one. Where's decimal point going to end up?
2.9.
It's going to end up here. But we have to write a scientific notation with the correct number of sig figs. If I write it as 2.998000000 times 10 to the 8, is that correct? No. Why?
Because the zeros aren't significant.
Right. They're not significant here because there's no decimal point. But once we moved that decimal point, they're to the right of a decimal point and to the right of a non-zero. Now they're significant. Now I have a whole bunch of sig figs here, whereas I only had 4 there. So in this case, I actually get to drop these zeros. The number here is exactly the same. I don't remember how many zeros I had, but that number is exactly the same as that number. So it's 2.998 times 10 to the 8. Scientific notation calculations, sig figs work exactly the same as we did before. When you multiply numbers in scientific notation, you do it in 2 steps. You do it for the numbers first, and then you do a second set of math for the exponents. So if you have 4.0 times 10 to the 6th times 1.5 times 10 to the negative third. First of all, multiply 4.0 times 1.5. Take that and separate it out. What is 4.0 times 1.5? It's 6. How many sig figs do I have to have? 2. There's 2 and there's 2. So my answer has to have 2. So it's 6.0 times 10 to the something. When you multiply exponents, you add them together. When you divide, you subtract the second one from the first one. We'll see that. So here we're multiplying. So what is 6 plus negative 3? 3. So it's this portion here, do the multiplication. 6 plus negative 3 is 3. You get 6.0 times 10 to the third. It's the same problem, basically, but division instead. So we pull out our numbers. What is 4 divided by 2? 2. How many sig figs do I have to have? 2. So I have 2.0 times 10 to the something. Now we subtract the second exponent from the first. What is negative 2 minus 3? Negative 5. When you take an exponent and you raise it to an exponent, again, you break it down into 2 portions. You're going to take the 3, raise it to the second power. Anybody, what is 3 squared? 9. So 3 squared is the same as 3 times 3, right? So how many sig figs does my 9 have to have? 2. 3.0 squared is the same exact thing as 3.0 times 3.0. 2 sig figs, 2 sig figs, answer has to have 2. So I've got 9.0 times 10 to the something. An exponent to an exponent, you multiply them together. So 4 times 2 is what? 8. 9.0 times 10 to the 8. Here's some examples. So this math is not hard, right? It looks scary, but you break it down into 2 parts and it's easy. What's the first step here? 6.78 times 5.55. Somebody has a calculator, tell me what that is. 37.629. How many sig figs do I have to have? 3. So what is that with 3 sig figs?
37.6.
There you go. 37.6. That 29 rounded down is now gone. So 37.6 times 10 to the what? 3 plus negative 4 is negative 1. How about this one? What's the first step here? 2.99 divided by 4.03, which is
12.0497.
how many sig figs do I have to have? 3. What's this in 3 sig figs? 12 point. I hear a bunch of things. 12.0. We have to round that way. 497 goes down. So we have 12.0. I have to get some new markers. times 10 to the what? So we subtract this one from that one. So it's -9 minus -6 is -3. That becomes -6 plus, -9, double negative becomes positive. -9 plus 6 is -3.
Wait, for number 2, we're dividing, not multiplying, right?
Yeah, so
Correct. So
why is
it,
it 12?
That 12 is wrong.
12 is wrong?
Yeah.
That's the point.
Because you someone multiplying it. It's
Point
0.74.
0.7 for 1. It's okay. Somebody's got to do it. It's 0.074 times 10 to the -3.
Okay, yeah, 742 actually, because the after the 1 is a 9.
Okay. 42, 10 to the negative. Is that correct?
No.
No?
Would it be 7.42? Times 10 to the negative 3?
You caught it. Yes. Has to be between 1 and 10. That is not between 1 and 10.
Wait, what's the negative 3?
Okay.
That should be 3.76 flat.
Yes.
Jesus.
Thank you. So let's start with this one. We'll go back to that. Okay. So what do we have to do to this one to get it between 1 and 10?
Move it to the right.
Move it to the right 1. So now we have 7.42 times 10 to the, what is it now? -2. So let's go back to this one. What do we have to do with this one? We have to move it to the left 1. So now we have 3.76 times 10 to the what? 0. So it's just 3.76.
Other one would be 10 to the -4. You move it to the right.
Yeah.
That's what I thought of it.
I was just trucking along and I questioned. I said, nobody's saying anything. It must be right. Well, I'm not going to take the time to think about it.
If you want to keep going, that first one's wrong too, because it's 12.0.
That'd be 1 point period.
We're just messing with it.
You know what's going on at this point, okay? Moving on. Number 3.
Number 3, right.
Science.
What's the first step here?
7 to the 4.
7 to the 4th. Anybody do that one in their head?
49 times 7 times 7.
Is
49
That'd
times
be
49.
the easy one for us.
49 times 49.
Like 1
2041.
Am I get that or something?
2004-31.
No,
401.
401.
401. Okay. And then, knowing this is incorrect, we're going to come back to that. Times 10 to the what? 12. 3 times 4 is 12. But this is not correct. So we need 2.401 times 10 to the
15.
15. We already have positive 12. You have to go another positive 3. 12 plus the extra 3 is 15. So I think the last thing we're going to talk about today is dimensional analysis. At first, it looks scary. But as you get into more and more complicated concepts and problems, it's going to be your friend. Like I said, it's math for dummies, okay? if you know how to follow a map, dimensional analysis will get you from where you're starting to where you're ending, and you don't even have to understand what the problem is talking about, okay? So dimensional analysis is your friend. The first step is to look at the problem and figure out where are we starting and where are we trying to go to. That's the first step. After that, we look at the problem and we say, okay, what directions does the problem give me to get from point A to point B? You do the problem, do the math, and then you just do a little checkup. You say, okay, does this make sense? If I'm converting 100 pounds to kilograms, and I do dimensional analysis, and I get negative 8,000 kilograms. That doesn't make sense, right? So you immediately know you did something wrong. So there are two methods. There's the grid method, which is what I use, and I suggest you use this method. The slides in the book use a different method with ratios. I think that might have been what you were thinking of earlier. It's the same exact thing. It's just how you write it. And I'll show you how identical they are, but they just, to your eye, initially they look very different. So very simple dimensional analysis. We're going to convert 2 inches to centimeters. What is our starting point? 2 inches. Where are we trying to get to? Centimeters. So then we look at, okay, what directions am I given to get from inches to centimeters? That's just conversion factor here. So, very first thing you do is you write where you're starting, 2 inches. And then you immediately draw a little T like that. Okay? You can extend that and draw an X, or a cross. So now you have 4 little corners. The unit here is always going to be that unit. Inches. That unit immediately goes down there. Okay? And we're going to turn this into eventually 5 and 6 steps. One step after another. And that unit immediately tells you what has to go there. So this is going to be our conversion factor. What's on the bottom here always has to be equal to what's on the top. When you go across a vertical line like this, that means multiply. This means multiply. When you cross a horizontal line, that means equals. So we have to have a conversion factor here with inches equal to something else. And we're trying to get to centimeters. In dimensional analysis, the unit that you're left with in the top right corner is the unit for your answer. So our answer we're trying to get is in centimeters, right? So we want the top right corner to be centimeters. Do we have a way to set inches equal to centimeters? I don't know if that's not on there, but you're not going to be asked that on a quiz. Or otherwise you'd be given it right here, right? So we can put in any number we want here. We can put any number we want here as long as it's equal to that number. So we're given that 1 inch is equal to 2.54 centimeters. That is my conversion factor. Now, when we have our units here and here, one on the top, one on the bottom, they cancel. The only unit we're left with is centimeters. So we know that our unit is going to be centimeters. Now we multiply everything on the top. Ignoring the bottom at the moment, we multiply everything on the top. So what is 2 times 2.54? 5.08. Draw a line, that's the top. Now we multiply everything on the bottom. This time it's easy. What is it? 1. So now we do that math. So we do 5.08 divided by 1, which is 5.08 centimeters. We're not done. What do we have to do? Sig figs. How many sig figs does my answer have to have? 1. 5 centimeters. Okay? So, you had, if you had no idea what inches and centimeters were, you had no concept of inches and centimeters, you could have done that problem. Just because you know 1 inch equals 2.54 centimeters. You did the math without knowing what the heck you were doing. Okay? Cancel units. Units are your friend here. Cancel them out. Make sure within the top right corner is the right number of units, and you're golden. That's exactly what we did. Okay. So here's another one. This one's going to be multiple steps. Look at the problem. Where are we starting? 2 kilometers. So it's going to be a learned skill to pull out of these problems where you're starting. 2 kilometers is at the end of the sentence, but that's where we're starting. Okay. So where are we trying to get to? Inches. We're trying to get from 2 kilometers to inches. So if we're starting at 2 kilometers, what is the very first thing I do?
Kilometers on the bottom.
I can put 2 kilometers, draw across a kilometers. I haven't even started to think about what math I'm going to do yet. I'm starting at 2 kilometers, and that kilometers has to be there. Okay? So now we can step back and look at the conversion factors that we're given and see if we can find a route from kilometers to inches. We don't have a direct conversion from kilometers to inches, right? If we did, we could do it in 1 step again, but we don't. So we have to do multiple steps. Even if you don't see the route jumping out in your head, we know we have to have kilometers here, right? Only one of our conversion factors has kilometers in it. So that tells us what our first conversion factor is. So 1 kilometer is equal to 1,000 meters. Our kilometers cancel. This unit immediately comes down here because we have to cancel it. So what conversion factor do we have that has meters in it? 1 meter equals 100 centimeters. Meters cancel. Now we're at centimeters. Now what can we do? 2.54 centimeters. Centimeters has to be here. Equals 1 inch. Centimeters cancels. We now have inches in the top right corner, which is what we wanted to have. So we're going to have equals something inches. So now we multiply everything on top, and we get 200,000. Multiply everything on the bottom. 2.54. We divide that by that.
78740.
78740. Is that right? Okay. So we have that many inches. Is that the correct answer?
No.
No. Why? Sig figs. 1 sig fig. So that becomes 80,000 inches. We round it here. 8 goes up. Right? So I think this then shows it, yeah. This is the other way. Okay? It's the same exact thing. You're starting at 2 kilometers. These are equal, these are equal, these are equal. I said when you cross a vertical line, it's a multiplication. Okay? It's the same thing. To me, this is easier to see. I like having that continuous line separating the top from the bottom. Here's another one. 14-pound block of gold, what is the volume? This one is more difficult. Okay. This one's going to make you think. This one's more harder than you will have on a quiz or a final exam. So if you don't immediately get this one, don't let your head blow up. So what am I starting at? 14 pounds. Right? I can do that without even reading the rest of the question. 14 pounds. Where am I trying to get to?
Grams per cubic centimeter.
He says, what is the volume? Right? So cubic centimeters. So I'm trying to end up with cubic centimeters. So the first thing that jumps out at me is pounds is not metric, right? And here we work in metric. So the first thing is going to be get this stupid 14 pounds in the metric. What conversion do we have that has pounds in it that'll get it to metric? 1 pound is 453.6 grams. By default, what goes here? Grams, right? So I have no idea what my next step is yet, but I know grams has to be there. So think about this. If you have a density of 19.3 grams per cubic centimeter, what relationship can you draw from that statement between grams and centimeters, cubic centimeters?
What do you want cubic centimeter from it?
Cubic centimeter should go on the
Well, you're on the right track. Grams has to go here. We have no choice, right? If I have 1 cubic centimeter, how many grams do I have?
Oh, 1 year.
19.3. There's 19.3 grams for each cubic centimeter. So for 1 cubic centimeter, I have 19.3 grams.
So you could.
So 19.3 grams equals 1 cubic centimeter. So I took this and I made my own conversion factor. 19.3 grams is 1 cubic centimeter. And now we have everything set up. Pounds cancel, grams cancel. You have cubic centimeters in the top right corner. If you didn't follow that one, don't worry about it. That's the book way to do it. Here's another one. Dan, every year, runs 6 5Ks. How many inches is 6 5Ks? And the only conversion factor we're given is 1 meter equals 1.09 yards. Everything else you have to know is something that you know. First of all, we're trying to get to inches, which is length, right? Are we starting with length?
Well, because aren't K's miles?
A K is a, what is it? What is a 5K?
5 kilometers.
5 kilometers.
That's six.
So if you run 6 5Ks in a year, how many kilometers does he run in a year? 30. Does everybody see that? 6 times 5 is 30. So he runs 30 kilometers. Okay. There is a way to get from 6 5Ks to 30 kilometers using dimensional analysis, but in that case, that's more complicated than what we just did. So there's no need to do that here. Okay, you're just going to confuse yourself. So at 30 kilometers, I'm starting at 30 kilometers, kilometers goes there. Now,
1,000 meters to 1 kilometer.
yes, we have a conversion factor that has meters. We know how to go between kilometers and meters. 1 kilometer equals 1,000 meters. That cancels, now we're at meters. In this case, we actually have to go from metric to English. Is it English units? What do we use? Standard units?
It's imperial.
Imperial? Is that
I think so.
normal units? Okay.
America.
So we have to go, we're now in meters. How can we get to American units? On the back of an eagle, right? That's how we get there. Is yards metric or American? It's American. So if we can get from meters to yards, we made that jump, right? We're given that conversion. 1 meter is 1.09 yards. We want inches. We're not given anything else. But now we're in American units, so now we know what we're doing. How can we get from yards to inches?
3 feet a yard.
36 inches.
You can either know that there are 36 inches in a yard and go straight from a yard to an inch, or how many feet are in a yard, 3, how many inches are in a foot, 12. So you can do it in 1 step or 2, depending on whether you know there are 36 inches in a yard. For fact that I'm out of room, we're going to do it in 1 step. So 1 yard equals 36 inches. Meters cancel, yards cancel, we're left with inches. We do the math. Okay? And at that point, it's just putting it in your calculator. And you all know how to use a calculator. Okay. Instead of doing this with the phone and everything, let's just work it through just like we were the other ones. We'll finish with a little bit of time left, and we can go over the homework again for the quiz. Okay? So, a baby aspirin is 81 milligrams. If you take a baby aspirin every day for 50 years, how many ounces of aspirin will you have taken?
Oh, what about the leap years?
You can choose whether you want to use leap years or not. So just take a minute and think about how you could start that.
There's either 12 or 13 leap years, depending on where the year starts.
Oh,
And if we use business or real dates of the year.
So,
Or how they survive.
If the first year was a leap year, then there's 13, but if it falls in the middle, then it's
it's the
12.
second week of class, so let's assume there's no leap year.
Ever?
Ever.
Betting if there's a shortage of aspirin.
So says the man up front. There are no leap years.
It's done very well, but.
what I would probably do, if I didn't know the year it started, I would probably say there's an average of 365.25 days in a year. That's as close as you can get without knowing how.
Then you get sig figs and that sorcery.
Okay, so where do you start? What number do you have to start with?
No.
50 years.
50 years. If you look at a baby aspirin is 81 milligrams. That is a statement, right? You can rewrite that. One baby aspirin equals 81 milligrams. That is a conversion factor. That is not where you're starting. That's just a conversion factor in words. So the only other thing here is 50 years. So I know this is going to get painful, so I'm going to start way over here. 50 years. Years goes here.
1 year is 365 days.
1 year is 365 days. Days has to go here.
I said 1 day, 1 aspirin.
There you go.
Oh.
That's the trick. 1 day equals 1 aspirin. Now you're home free. So aspirin has to go here for rin. Now what can I do?
One aspirin is 81 milligrams.
1 aspirin is 81 milligrams. Milligrams goes there.
1,000.
1,000.
Right. So now I'm in milligrams. I have to get the ounces. Ounces is where I'm going. And I know how to get from grams to ounces. And we know how to get from milligrams to grams. So what number goes here? 1,000 milligrams equals 1 gram. Gram goes there. 28.3 grams equals 1 ounce. Is that right?
If you take sig figs, 52.
52.
Would it not be 52.2 because the gram says a 0.3 at the end of it?
I don't know. It's only 81 milligrams.
Think,
Well, now aren't we going to ounces?
We have to go off the 50, and it's only 1 sig fig.
You're right.
there you go. We only had one number to start with, 50. Everything else was conversion factors, and like you alluded to before, you ignore sig figs and conversion factors. So the only number we had was 50. And it's not 50 point, it's 50. So there's 1 sig fig. So it's 50. So basically you take an ounce of aspirin a year.
That makes me so mad.
What does?
Like how it's like you did all that just to try not get the actual answer that you got. Like you have to
Yeah. But, I mean, the guy... Well, actually,
It'd probably still be 50.
it'd probably be 50. You probably round it out at the end anyways. In actuality, you probably, we'll learn in lab, the number of sig figs comes from how precisely you know the number. This person, they know they took it for 50 years, which would be 50 point. So when we'll learn this in lab again, but when you say 50 without the decimal point, that means anywhere between 45 and 55.9. You don't know where in that range. Okay. But in this case, you actually do know, so it would probably be 50 points, and so you would have 52. Okay. So I think that's the end of it. So we want to start the quiz.